You know, the idea of a function. We won't go very long today because, well, we don't want to strain ourselves day one back. But functions, what are they? Standing feature. Give me a definition. Put something in, you get something out. All right, that's cool. Okay. So like a pop machine.
It's kind of like what?
It's kind of like a pop machine. Okay. Alright, so you push the button. You push the Pepsi button and the Pepsi should come out. That'd be nice. It would kind of irritate you, would it not, if you push the Pepsi button and Diet Mountain Dew dropped out, yes?
Unless you wanted the diet.
Then you would have pushed the Diet Mountain Dew. The point is when you push a certain thing, you expect something to happen, yes? And you expect it to happen that way every freaking time. You don't want any surprises. You don't want to go to Taco Bell and you walk into dinner and the little gal in front of you goes, hey, geez, I'd like 10 tacos. And she's like, and it's like $7.90, great. And then her girl walks in and goes, I want 10 tacos, $20. What? 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 And for me, it's always bothered me when people are like, oh, it's so hard, functions are so hard. No, they're not. You do the same thing, the same result should happen every single time. Now, is it possible? So, you know, the actual definition, of course, is what? For every x, there is what? There is how many y's? 1. And in particular, big boy mathematics here, 1 and only 1. Why? Does that mean the y's are unique to every x? No. No, because each of the x's can share the same one, for instance, right? What happens if you drop a piece of this nice round steak? Drop it through the meat grinder. What do you get? You get hamburger. What if you drop this nice round roast through it? Oh, you get hamburger. How about a sirloin steak? Hamburger. You get hamburger. What if you drop your finger through it? Ooh, hamburger. Now, you get hamburger. It's the same. Different inputs give you the same output. That's possible, right? Going to it used to be back in the drive-in movie days. No one really knows what a drive-in movie is. But going to the old country buffet or whatever, one of those buffet places. It's $10. It's all you can eat. What about Grandma? She eats like a half a plate of food. It's $10. He's coughed it up. What about Corey over here? 10 plates. He's on his 11 plates. $10. Me personally, I always felt like I had to eat extra to make up for what Grandma didn't eat. Personally, I felt that way. But you know, the idea that each x has one and only one y. There's no chance that this x could get two different values of y out of the thing. That's the huge concept. And then, you know, we talked before about the idea of inverse functions, right? What makes it possible for us to do an inverse function? In other words, can you run the meat grinder in reverse and turn your finger back into a finger? A hamburger. Come on. Because it has no idea where it came from. Meat grinder just grinds meat. That's all it does. However, though, if you you send a bag through the baggage claim area and you turn the machine on reverse and out comes your same bag. It didn't like change into something weird. It just was going down a conveyor belt. You turn the machine, it came backwards. Oh, look, it's my same suitcase. It came off the belt. It's all the same. So some functions we can inverse and some functions we can't. And so the idea here is what? It's a one-to-one relationship. One-to-one. That is, each x has one y. One y, and each y has one x. Monogamy, if you will. Okay? No, none of those cross. You know, nobody mixes over both ways. So the idea of an inverse function. So it's kind of a good thing, right? If you, I don't know. Let's see. What would be a good function on our calculators? One that we know. Yeah. So if we times by 3, the inverse of that is dividing by 3. That's real nice. You can't screw that one up. What about squaring a number? X squared. Does he have an inverse? Well, x squared looks like this guy, right? Okay. Clearly it's a function because it passes what? You remembered I taught him something. The vertical line test. That's sweet. Passes the vertical line test. Will its inverse be a function? Why not? Why not? Nice, because it doesn't pass the horizontal line test. That's right. Because this particular value of y, for instance, right there has what? Two values of x. So does the number y equals 4, for instance, does it match up with 2 over here, or does it match up over here with negative 2 for x? No idea. How is it then on our calculator when I go, okay, 2 squared, or yeah, equals 4, and then I go square root, why do I get 2 back? Why is it the calculator just doesn't go, hey moron, I don't know? Why is it that it's able to give me a number back? One of them. But it's not technically an inverse unless it passes the horizontal line test. And so what happens is, and we're going to spend quite a bit of time reviewing this, is we restrict the domain. And we say, hey look, we're going to make this function be x squared, but where x is bigger than or equal to 0. Now does this function pass the horizontal and the vertical line test? Sweet! Now she has an inverse. Same thing is true with the sine function, right? Clearly it's a function. Its inverse is clearly not. That goes through the origin in case you're wondering. Clearly its inverse is not going to be a function. But we can fix that by taking the little eraser here and going, let's chop it here and here. Does that take care of all my values of x or all my values of y? In other words, from -1 to +1? Yeah. It's got them all. And so we restrict the domain here, the sine function, such that it's between -π/2 and +π/2. Okay, it's just some things like that. We're going to spend time going over, make sure we're all on the same track for that. Because in calculus, domain matters a lot. The fact that it is a function matters a lot. The fact that we talk about continuous functions matters a lot. It's all going to hinge back on our basic idea of functions. Let's see, what else? A little quick review things today. What about, we have two functions, f of x plus g of x. What do they want us to do here? What do they want us to do with these two functions? What is the function f? What? Oh, I don't know either. What do they want us to do with it? What's g? I don't know, but what are they really wanting us to do? Before we know anything else, what do we want us to do? So if I had two functions, I mean, suppose we had this function here. Suppose this was f, and this was g. -2x minus 7, or something. And you want us to add them together. What do we end up with when we add them together? X minus 5. Nice. And that's no big deal. But what does that really mean on a graph? Huh? 3x plus 2 is here. And -2x minus 7. Oh, geez. Nice job, Jay. Sweet. So when I add these two functions together, what am I really doing? I know I end up with x minus 5. X minus 5 looks like here and has a slope of this. That's what it says when I add them together. It's the new thing I got. But what does that have in relationship to the other two, graphically speaking? Well, if you recall, come back into here. What happens when I add this y value to this y value? Well, this is -7. This is +2. When you add them, what do you get? You get -5. Okay? Here is, right here, a y value. Here's a y value. What do you get when you add them together? You get this y value. Okay? And at some point over here, they're going to have, one of them's going to have negative something, the other one's going to have positive something, but it's exactly the same. And when you add them together, what do you end up with? You end up with a 0. Okay? And so that idea that graphically, we're going to need to look at it both numerically, obviously adding the functions together. We're going to need to look at it algebraically with the actual functions, and then graphically as well. We're going to spend a lot of time with that in this first couple of chapters. Going back over that, make sure you're all on the same page with that, because once we get into the calculus part, it's going to get ugly. Okay? And if you don't understand that part of it. I threw the name up there a minute ago, but domain, what is it?
All the x values.
Yeah, all the allowable x values. How would I know if they're allowable x values? How do I know if they're allowable or not? Oh yeah, in the past we've been told that. So as we move into calculus, how do we know if it's allowable or not? So if I just, where's a function we might run into trouble with? Here's me. What is a function we might run into trouble with x values? I don't know. It's fine.
Oh, I don't know.
Ooh, yes.
Like, what's it though? Like a sine curve that's above the x-axis, or like a sine function that like it's like all on the top and it's not crossing the x-axis.
So it wouldn't have any zeros. Is that what you're saying?
Yeah, so like, it's like
But is it? But couldn't I still put in the x value? I'll put in an x. I'll still get a y, won't I? Is there any functions that I can put in an x and I'll get some weird y out that I wouldn't be cool with? Yeah.
I mean, allowable
That's
is
all connected. What?
all real numbers.
On a lot of functions, yeah. On a lot of functions, but not all functions, right? Because I like the idea of a circle, right? Here's a circle. That's cool. Something like that. Let's give them a radius of 2. How cool is that? Put in any x between 0 and 2, and you're good to go. Between negative 2 and 0, you're good to go.
wait, are we still talking about functions?
Okay, I didn't say it was a function.
Okay, then never mind.
But what I'm talking about is this. Are there values of x that we can't use here? Any function that's what? Any value of x that's greater than what is going to cause us a problem? Any value that's bigger than 2 is going to cause us some issues. Because, and let's actually make it a function so Spencer doesn't have a heart attack. Now it's a function, yes? Now it's a function? Yes, it is.
Yeah.
This function would look like this. So the circle itself is x squared plus y squared equals 4. But if you solve for y, you get this. Y is equal to square root of 4 minus x squared. Why is it that x has to be less than 2? Less than or equal to 2? Because you get a negative in a radical. You get a negative inside the radical, which gives you an imaginary number, right? So for allowable values, remember, that means that our y values, or our range has to be real numbers. So any x that doesn't give us a real number for a y is going to be a problem. So in this case, anything bigger than 2 or negative 2 is going to cause us an issue. Okay? What other things can give us problems? Square root's always going to cause us problems, or potentially cause us problems. What else?
Y equals 4.
Y equals 4. What's the domain of this function? This is the buffet function. Right? How much does it cost to eat the buffet? $4. Does it matter how many times you go through the line? No, because x isn't here, right? So we're good. X would be all real numbers in this problem, right? Any real number gets the job done. Could x be pi? Could it be negative square root of 2 pi? Of course it could, okay? Because x isn't here. How about this? Let's actually do this in honor of the Scappoose kids being here. How long does it take to drive to Scappoose at X miles an hour? Okay? I don't care how fast you drive, it will take you some time to get there, yes? Even if you're in an F-18, you're doing about Mach 2 coming overhead. Stop the watch, hey, you're there in about 3 seconds. But it doesn't take no time. It always takes some amount of time, okay? You can't get there. In other words, what could X not be here at this point?
0.
Yes, X, it better not be 0. So, anytime, and this is going to hold throughout forever, Domain problems are going to result typically from, come on Betsy, domain issues are going to arise typically from even powered roots, fourth root, square root, and so on, and rational functions that is x is in the denominator. Okay, typically those are where we're going to have issues. And they aren't going to tell us anymore, okay, because they assume you're big boys and girls now, and you're going to know that. So it won't say, look, x has to be this between here and there. You're going to have to just look at it and know. That's cool. X is in the denominator. Yeah, if I abbreviate too much, let me know. We good? Denominator. Okay? So like on this problem here, okay, the domain of this function, in other words, is there anything that x can't be? And by the way, oftentimes as a parent, I think it's easier to tell kids what they can't do than what it is that they can do. Okay? Robbie's going out tonight. There's like two things I don't want you to do. Is Robbie's dad, I don't want you to hang out with Spencer and Kenny. And I would like you, good. And I'd prefer that you didn't drink and drive tonight. Okay, there's like two rules for him. It's easier to tell him what I don't want him to do than it is all the things you can do. Now you could go to Target tonight. You could go hang out. You could go cruise for chicks at the Dutch Brothers thing or whatever. You could drive the lawn. You could go bowling. You could tell them all these zillions of things. But there's kind of an infinite number of things your mom and dad are pretty happy with you doing. But there's probably like only two things, you know, the Spencer Kenny thing, perhaps, and the drinking and driving. Those are the things I don't want you to do. So oftentimes it's easier to tell you what I don't want you to do. So in this case, is there any function or any value of x we don't want? Well, yeah. So 2x plus 5 better not equal 0. So x had better not equal negative 2.5. And I'm kind of a fraction fetish person, so I'll leave them as fractions most of the time. But if you like them as mixed numbers, you knock yourself out. Okay? So, you know, we're going to come back and really come back to that a lot over the course of this term and see, make sure we're on top of that domain-wise. I think two more things before we go today. Very much just a big picture day today, so don't sweat this too much. Now, calculus really is divided into two things, all right? We're going to be talking a lot about rates. And later on we'll be talking a lot about areas. And those are the two overarching areas of calculus right there. That's it for the first two terms. But what is a rate? In your layman's terms, what is a rate, Olivia? Me? No, it's x. This is a variable. No, I want a rate, lady. Give me a rate. What's a rate? Yes, you do. That's why I'm asking. Give me anything. Suppose there was a wrestler who got a certain infection, and you measured the rate at which the area spread across his body. Now tell me, what is that saying? What is the rate in that case? Wait, what is it? I mean, that's what we'd be talking about, right? You like all of a sudden it like grows over the top of his head or something. I'm just saying. What? Wait, okay, so it has to do with time. It has to do with time, but what? Change. I hear the word change. I like change. Change in what? Change in what?
Change over time.
No, distance. Okay, so driving down the highway would be distance over time. I like that. Okay, Again, this poor guy had a little bit of infection here, and then all of a sudden it's here, and then it's here, and then it's here, and oh my gosh, his whole head. It wouldn't be so much a distance, it would be what? It might be more of a what? An area?
Yeah.
Okay, if it was a tumor, it might be more of a mass. But yeah, you get the idea. So it's change in, so delta, it's a triangle, it's the Greek letter delta, means change. The change in distance over time. Could be that. Could be the change in area over time. Could be the change in, what else you say? Change in mass over time. Could be the change in the number of tardies over time. Could be a lot of things, but it's always going to be the change in something, usually per unit time. Okay? In the real world, everything is time and money, right? I mean, we laugh and we joke, but that's really what it boils down to, right? If you can do anything today, what something that you would like to do today, what's going to really be the boil down factor of it? I mean, why can't you do it? There's going to be typically 2 reasons. That's it. I would really like to do this today, but I got cross-country practice at school, and then we got to have this, and I got to do calculus homework, and I have to do that homework, and there's no time. Or I'd really love to go do that, but it's going to cost $150, and I just don't have it in my pocket. It's always going to boil down to, in life, one of those 2 things. Now, on a graph, a lot of times it's change in y over the change in x. That's just the definition of slope. But in reality, a lot of times we're going to be dealing with time. So we're going to spend a lot of time this year talking about rates, a lot of time. Kind of a big deal, you know. We'd like to stem the growth of that thing, right? In real life, we'd like to know. Okay, so I was reading a thing the other day. What was that about? Something about when a nuclear blast goes off. If you're how many miles? 2 miles away, you have 20 minutes to get out before the fallout comes down. But the little fallout, you know, when the nuclear device detonates, right? And if they don't detonate on the ground, but suppose it was on the ground, you know, it's got to go up in the air and around and get around to get to you, right? It's not going to come straight line at you at 60 miles an hour or 100 miles an hour. Because if it was, it would be linear functions, and that's really boring, okay? Divide the distance by 100, done. There's how long it takes to get here, piece of cake. But in general, it doesn't work that way. In life, you know, things are kind of goofy. I go to see my parents, it's 300 miles from here, it takes me about 5 hours. Geez, Mr. Young, you drove 60 miles an hour like a robot all the way through. No, I didn't. I stopped, I got an ice cream cone, I had to stop 4 times for the kids to pee. There was a traffic jam, I got a speeding ticket. So I was driving 80 most of the time when I was actually driving. I just happened to be that it took me 5 hours, so I averaged 60 miles an hour. But in fact, my speed might have very well done this. I kept going, I sped up, I kept it constant, I stopped for a long time. Wow, that looks like I ran into a wall. I'm sorry. I came down to a nice stop and then held her constant for a while. And then maybe I sped back up and held her on cruise control and then, whatever. Yeah, we don't know what it looks like. We know that the average might have been 60 all the way across. But, that idea of those rates of change all the way through. And then we'll do some areas later on in the second half of the year. But those are the 2 overarching areas of calculus, or pieces of calculus. By the way, they won't be like an area of a rectangle, because that would be really boring. You go back to 3rd grade, 2nd grade. So, it's obviously going to be some goofy, weird shape. Find the area under this curve. Oh, okay. Cool.
Where does it end?
What?
Where's that end?
Right here.
Okay.
By the way, that's an excellent question, Kenny. What if it didn't end? What kind of area would you have?
A lot.
We prefer the word infinite. But yeah, good. Find that one. Yeah, you can't, so you'd be screwed. Yeah, that'd be exactly right. That's a good question. What if it didn't just look like this guy? What if it looked like this guy instead? Here's your function. It's coming along, and just how far up does that sucker go? That's an asymptote right there. It goes up forever. So quick, find the area between here and here. How high is it over there? It goes up forever. But it's really skinny, Mr. I don't care. It goes up forever. So what's the area? Hey, I can't find it. Now between here and here, piece of cake. All right, see y'all tomorrow. We'll get going in earnest then.